Welcome to my Lab 3 report for Physics 2211. In part 1 of this lab, we were to analyze a star's motion and orbit around a black hole to determine the mass of that black hole. We used our fundamental principles, Newton's law of universal gravitation, Newton's second law, and the momentum principle to create a computational model to solve for Fnet and determine the mass of the black hole. In part 2 of the lab, we had to determine what initial velocity our spaceship would need to have to leave a planet orbiting a black hole and fly around and away from the black hole. Using the same fundamental principles as before and the position update formula, I will determine the desired velocity. When analyzing both parts, I aim to understand the difference between using Fnet and the rate of change and their components, and also what might happen if, instead of flying our ship away from the black hole, we try to keep it in orbit around it. Let's start with part 1. Our system is our star, which has a mass of 2 times 10 to the 30th kilograms, and its position and trajectory are uniquely generated in the starter code. Our time interval is 86,400 seconds, and the mass of the black hole is unknown. We can use Newton's law of universal gravitation to solve for the black hole's mass, but we need to know the net force. To do this, the fundamental principles I used were the momentum principle and Newton's second law. The change in momentum equals Fnet times delta t, and Fnet can be split up into its parallel and perpendicular components. The derivative of this formula gives us the updated formula. dp dt equals the parallel component, represented by a change in magnitude of the momentum times the direction of p hat, plus the perpendicular component, which is the change in direction times the magnitude. Using the glow script starter code, I plugged in the star's mass, the time interval, and created calculations using different equations. Defining our initial and final momentum, our delta v and delta t, I used those in Newton's second law to create equations for Fnet, Fnet parallel, and Fnet perpendicular. With this, I made an equation to solve for the mass of the black hole. I ran the code and got a resulting Fnet, Fnet perpendicular, and Fnet parallel. Throughout the orbit, you could see that it gives many different values for the black hole's mass, so I made a calculation to give me an average of those values, which is 1.07 times 10 to the 34th. In part 2 of the experiment, we had to determine an initial velocity that our spaceship had to have to leave the planet, fly around the black hole, and escape the orbit. We use the same fundamental principles to solve this problem. However, we need to calculate all of the forces on the planet and all of the forces on the spaceship. Following the provided starter code, I plugged in the black hole's mass from part 1, increased the total time, and plugged in all of the equations necessary to solve for all the forces on the planet and all the forces on the spaceship. I also plugged in the necessary position update formulas to make the spaceship and the planet move. I started by plugging in numbers and watching the results and working my way up. I found that the minimum y velocity I needed to escape the planet was 2.08 times 10 to the 6 meter per second, and the minimum x velocity for the ship to not crash into the black hole was negative 2 times 10 to the 7th meter per second. Running the simulation, we can see that our spaceship leaves the planet, gets very close to the black hole, and flies away. What does it mean? Looking back on our calculations for part 1, we had to be careful about differences between net force and its parallel and perpendicular components, and the rate of change in momentum and its parallel and perpendicular components. The net force and its components describe the actual forces involved in the equation, while the rate of change in momentum and its components describe the effects of those forces, and you can use them to calculate for the net force. You can think of it like the wind in the trees. You can see the trees moving, which is observing their momentum, and you can understand that there is an external force, the wind, that is moving them. What if? In part 2, what if we wanted the spaceship to stay in orbit around the black hole? I took the code and used more trial and error to see how changing the velocities in different ways affects the ship's trajectory. I found that mimicking the orbit of the planet was a good way to go, so I made my ship's y component slightly faster than the planet's orbital speed. My y component was 9.5 times 10 to the 6 meters per second, and to offset the orbit a little to prevent collisions between the planet and the spaceship, I made the x component negative 2 meters. Running the computation, the planet and the spaceship complete a full orbit without colliding, making my mission successful. Thank you for watching. Goodbye.